So, hello everyone, we are back, and in this class, we will be studying two very important application area. One is in the area of plasma medicine, and another is application of plasma in the area of agriculture. So, the first one, plasma medicine. This is an emerging non-thermal plasma medical technology. Now, about the cold atmospheric plasma in medical applications, these are the important points to note. The cold plasma works at near room temperature. Near room temperature means it may not be say 20 degree or 30 degree centigrade. It may be a bit higher than that, but it is within the acceptable limit by living cells. So, they will not be harmed by the temperature of the plasma. You can very well touch the plasma by your hand. Now, these plasmas are minimally invasive and they are non-toxic. So, this is very much important thing, that they should be non-toxic. Usually, it is a reactive oxygen and nitrogen species, we call it RONS, through which they interact with the living organisms. They induces apoptosis in cancer cells. So, this is a way by which the cancer cells are killed. They disrupts the microbial membrane. So, this is one way, the route to kill the microbes. They stimulates tissue regeneration. They are very important and useful thing, tissue regeneration. They work very wonderful for wound healing, sterilization, disinfection. Of course, the other things which we called this apoptosis and disruption of membranes, they basically belongs to this cancer therapy. Skin diseases like psoriasis, eczema, this cold plasma can be used. In dental treatments, now this is almost going to be a regular instrument in dental clinics. Then selective cytotoxicity, toxicity against tumor cells. So, this is actually a very important aspect, because when we want to kill the cells, we want to kill only the cancerous cells, not the healthy cells. So, selective killing of the cancerous or malignant cells is very important. Now, how do they do? They do it through induction of oxidative stasis. They promotes immune response against tumor and then accelerates healing of chronic wounds. Promotes again angiogenesis and cell proliferation. How do they do? What is that angiogenesis? Basically, this is the the routes to distribute your blood, so veins and capillaries. So, in angiogenesis, you get more such capillaries grown through the process. So, here you are seeing one example, so through which the blood vessels, basically new blood vessels are created, and in your cell proliferation also some new cells get created in the process. So, because of the antimicrobial activity of this cold plasma jet, they can reduce the microbial load as well. Now, here I am showing you one example of actual cold plasma jet operating, and how do they differ from other devices and what is their potential. Now, see, on the left hand side we do have one radioactive source. All of you know the radiation therapy. So what are the agents by which they impart the effect? So they are alpha, beta and gamma, all of you know. So they are the basically agents which are coming out from a radioactive substance. Now what is alpha? So they are nothing but the helium nuclei. Then what is gamma? They are electromagnetic waves. And what is beta? They are electrons. Now when you are having a radioactive source, for example say cobalt 60, you know the gamma that is coming out from them, they are having very precise energies. You can't vary them. So wherever you take the radioactive source, you will be getting emission of gamma at that energy level only. For example, in cobalt 60 you are getting at 1.17 3 MeV and 1.33 MeV. So they are very precise energies. Now suppose you are producing a helium plasma, then what you are getting? You can get helium ion. So if you are able to doubly ionize that, then that is nothing but your alpha particle only. And then as you have created a plasma, it is full of electrons, they are nothing but the beta particle, and the electromagnetic radiation is a part of the plasma whenever is generated. So that is nothing but the electromagnetic radiation. So basically you are capable of producing all the particles which are getting generated in a radioactive source, but the energy range is way different. For example, here you are generating the ion mostly at your room temperature. Here it is in MeV range. And the electrons here, it may be say few electron volt only. That is the limit. It may be 2 eV, that may be 3 or it may be 3 eV, not more than that. But the interesting thing is that you can control their energy as per your wish. You can make a change in the atoms. For example, here you are in radioactive case, you are forced to use only one type of atom, that is helium nuclei. But here in the plasma, you can use many other atoms in the periodic table to produce plasma, and you can try to check what is their effect. And this area is just emerging, so not all studies are done, but the effects are gradually coming prominent. As I told you in the previous slide, that it is the oxidative and nitrocytative stresses through which these devices basically work in the biomedical application. Now when you see that this device actually called atmospheric plasma device, it is called CAP device, when it is interacting with the air, apart from the species that it generated over here, that is helium, argon, electron, it can generate many other pieces, like it can break the nitrogen atoms, molecules, and produce nitrogen atoms. Similarly, it can get oxygen atoms, they can combine together, they can form O2, or they can form NO, and then NO is the agent which is signaling molecule in case of biomedical application. It can produce H2O2 as well from the hydrogen and oxygen reaction. So that is having enough antimicrobial activity, and this nitrate and nitrates also can produce. And there is another radical which is produced OH, which is very dangerous for the human cells or living cells. It can rupture the membrane. So all these agents are there to influence the biomedical application. And when the device operates, you are seeing always on the right how the device operates, and when you are going to apply on that human cells or in some liquid which can make plasma activated. So they are done always at temperature which is bearable and within the this human cell bearable limit. Now here is one example of effectiveness of this plasma jet, cold plasma jet in case of breast cancer cell lines. What you are seeing here, that initial colony, this is study 1 and this is study 2, we call it replicate 1 and replicate 2. Initial colony is like this, then untreated cells after 48 hours. It goes like this. Then cells treated with cold argon nitrogen plasma. Sorry, this is gas. This is no plasma, only gas. And you see that for 10 minutes, after 48 hours, it goes like this. So the cells are alive. But when you treat that with the argon nitrogen APPJ, that cold plasma, atmospheric pressure plasma jet, cold plasma for 10 minutes, you see that all the cells have been killed. So this is the amazing effect of this cold plasma discharge over the cancer cell lines. So you can see that they are really effective. Okay, so this blue is actually shows the color of the dye that has been used to note their colonies, and these colonies are completely destroyed in 10 minutes after you treat that with argon nitrogen APPJ. So this is just to give you one example, one interesting area where this application of cold plasma is increasing day by day. And with this actually I stop here and switch to the plasma agriculture area. So in this area I'll tell one application where you are synthesizing fertilizer, nitrate and nitrate fertilizer using plasma. You know, our environment is full of nitrogen gas. More than 70% of our atmosphere is consisted of nitrogen. And still, when a plant needs nitrogen, they cannot take it from the atmosphere. It is something like that, water everywhere, nor any drop to drink, what Samuel Taylor Coleridge told in his poem about the ocean. You cannot drink a drop of the water. Similarly, the plants, although they are immersed in the nitrogen, they cannot take a single molecule of nitrogen out of that. Why? Because nitrogen is having a triple bond which is extremely strong, and it cannot be broken so easily. So how plant gets nitrogen? So it is the process by which nature provides nitrogen to the plants, while lightning, because of the very high temperature in this plasma that is created, N2NO2 joins together and form NO. This NO finally forms HNO3, and that through the rain comes to the earth, and that nitrate can be absorbed easily by the plants. Now, in the natural cycle, actually, this nitrogen fixation happens like that. There are nitrogen fixing bacteria which forms the ammonium ion, and then this ammonium from ammonium ion, this and ammonia, there are nitrifying bacteria which forms the nitrate, and that nitrate is absorbed by the root. So this is assimilation process. And there are other bacteria which are called denitrifying bacteria, which takes the excess nitrate and makes them they free the nitrogen to the environment, and that nitrogen again comes back to the plant through the nitrogen fixing bacteria. Now this process, natural process, is not sufficient many of the times, and our farmers require to apply additional commercial fertilizer for their cultivation. Now there are different routes by which this is being provided. One is ammonium nitrate route and calcium nitrate, and another is urea. In most of the cases, urea is applied to the field by the farmers. Now ammonium nitrate and calcium nitrate, they are exceptional source of nitrogen due to the fact that they have a smart nitrogen balance. Half of the thing is say ammonium nitrate. There what you are giving, ammonia ion is half the part and nitrate is half the part. This nitrate is readily usable. That is a very fast process and can be directly absorbed by the plant. On the other hand, the ammonium ion is taken by the nitrifying bacteria in this site, and this is slow process. These bacteria converts this ammonium ion into nitrate, and that is absorbed by the root. So what is finally absorbed by the root is the nitrate ions, NO3 minus. And how urea works? Urea, formula is NH2CO NH2. In contact with water, they at low pH they form ammonium carbonate. This ammonium ion is there, then this ammonium ion is taken by the nitrifying bacteria and that forms nitrate and that is absorbed by the plants. There is another route which occurs when your pH is high and temperature is high. The previous one where ammonium ion is produced, this is done at low pH and low temperature. But the second one, when the pH is high and temperature is high, this ammonium carbonate, which this doesn't form the ammonium ion, this breaks into ammonia, and when it breaks into ammonia, then this ammonia is lost in the atmosphere. So depending on the pH level and the temperature of the field, the usage of urea depends. The absorption or formation of nitrate from the applied urea depends on the pH and the temperature of the field. Now, urea is produced using the Haber-Bosch process. So, the process is that N2 plus 3H2 is equal to NH3. So, this is the basic process, and this NH3 then interacts with CO2 and forms the urea. So, this is the basic process, and this is the kind of setup people use. And this ammonium ion, this comes when NH3 and H2O interacts, and this ammonium ion then taken by the nitrifying bacteria and they form the nitrate. So, this is the overall nitrification reaction. Now, what are the drawback of the Haber-Bosch process? So, it is a very high temperature and high pressure process. Its temperature requires is around 450 degrees centigrade and the pressure that you require is 300 bar. It consumes around 1% of the world's total energy supply at present. Then it accounts for 1% of global annual CO2 emission. So, this is really a concern for the society, and this actually generates 1.9 tons of CO2 per ton of ammonia production. So, at the basis, Haber-Bosch process produces ammonia, and from that you are converting that into urea, NH2CO, NH2, and that process requires high temperature, very high pressure, that consumes a huge amount of world's total energy supply, that produces 1% of the global CO2 emission. So, this is something where our society is concerned, and the holy grail is that zero carbon emission nitrogen fixation. This should be green and sustainable as far as the chemistry is concerned. So, in this scenario, the major issues what we find that the Haber-Bosch process is non-decentralizable, cannot operate with intermittently available renewable energy sources, uses fossil fuel derived fuels as source of hydrogen, hence not sustainable because it is using fossil fuel. Then it has significant impact on economy as it involves cost for transportation. Because of so bulky equipments are used here, you have seen that the kind of pressure they require, kind of temperature they require, the kind of installation that is there, you see the installation that is there, the components they are using, they are not decentralizable. So, you need to produce at one place and then you need a transport mechanism to transport the raw material and distribution of the product. So, ammonia storage, that is what is produced there in the process, that requires high pressure at ambient temperature or negative temperature minus 30 degrees centigrade under atmospheric pressure to store that. So, that invites additional cost. So, in this scenario, the plasma method works like this. Plasma induces excitation, vibration, dissociation, oxidation and reduction of nitrogen and dissolution of the nitrogen fixation products at the plasma liquid interface. Then what it does? Plasma allows direct interaction of water and nitrogen to fix the nitrogen. Depending on the type of plasma catalytic system, plasma can instantly fix nitrogen in the form of nitrate or nitrite. In presence of catalyst, plasma catalysis may enhance the fixation rate by manifold, a highly reactive area of research at present. So this is basically the process by which the plasma basically fixes the nitrogen in water. So what are the influencing factor? Plasma category, whether it is thermal or non-thermal, pressure, whether it is atmospheric, low pressure or high pressure, volume, what is the large volume or a small volume plasma or a film plasma like DVD discharge, plasma temperature, whether it is a gas temperature, what is the electron temperature, then nitrogen source, whether it is a pure nitrogen from a cylinder or a plant or it is taken from the air, oxygen, whether presence of external oxygen or oxygen from water alone, whatever is coming there. Then the discharge type, DVD discharge, pulse discharge or it is an arc discharge. All of them can produce, but only the production rate will be different. Then the power source type also matters, whether it is AC, DC, pulsed or what is the power level and what is the pulse height. Then reactant type like H2 vapor, H2 droplet, aerosol, H2 liquid, all these things actually matters the synthesis. So here I have shown a simple synthesis process. So this is a plasma torch which is discharging the plasma jet. It is taking air from the atmosphere and converting that into plasma. That this is a reaction chamber where the catalyst is present, and this part I have shown it in a expanded form over here. I will come to that. Then as the plasma interacts with the water that is flown to the region by this pump in the form of a mist, so that interacts with the plasma, air plasma interacts with the mist in the presence of the catalyst and fixes the nitrogen. That nitrogen fixed water comes here, then it is recirculated back into the reactor zone and the concentration keeps on increasing as the cycle continues. That the water comes here and then pump via the pump, that is again pushed back to the reactor region. The cycle continues and the concentration keeps on increasing. Now in the reactor design how it works, so here the plasma N2A plus O2 forms the air plasma over here in this zone, that is shown over here. Then that interacts with the water vapor, water mist that is injected into this zone. They forms water vapor, breaks the water H2O into H and OH, H plus and OH minus. That interact with the water and the air and the broken nitrogen species and the broken oxygen species in presence of the catalyst and forms the nitrate and nitrate fertilizer and comes to the tank where it is being stored. Okay. So and that water from the tank again recirculated back to this zone, to this water mist that is formed over here in this plasma water interaction zone by the catalyst. Again that is interacting and producing more nitrate coming to the tank and again circulated back. So this is the way the concentration getting increased. So some of the distinctive feature of this process is that in a single step the thermal plasma produces air plus water is equal to nitrogen fertilizer. So what are the ingredients? Air and water. They are plentifully available in the nature. Such process is equivalent to continuous lightning process under optimized condition, giving synthesis rate several orders of magnitude higher than that achievable in competing non-thermal plasma processes. The main difference is due to the fact that in thermal plasma you are getting a species concentration of the order of 10 to the power 24 or so, whereas in non-thermal plasma you are getting a species concentration around 10 to the power 19 to 10 to the power 20 at most. So you are having a 5 orders of magnitude difference in the species concentration itself. So that is basically causing the fixation rate, a drastic difference in the fixation rate, and you are getting much higher fixation rate compared to non-thermal plasma, and the rate of production of nitrate may be different by a factor as high as 65,000 times. That has been seen in recent literature. So it is not using any fossil derived chemical, so it is sustainable, directly converts freely available abundant atmospheric air into nitrate and nitrate through interaction with water in a very efficient and low cost controlled catalytic plasma environment. It completely avoids production of greenhouse gases like CO2. That is very important. You have seen that the enormous amount of CO2 that is being produced by the Haber-Bosch process. Now, thermal plasma catalyst based technology easily offers reactant density at least 5 orders of magnitude higher compared to non-thermal plasma. As I have already told you, the highly portable system, because the system is very small, as you have seen, the whole system looks like this. It is a tank, and the dimension you are seeing, it is less than a meter. So you can understand what a meter looks. So it is less than a meter. So you can see how compact it is, and it is wheel mount. You can take it to any place wherever you want. Now, so I was here. The system offers a clean, sustainable, decentralizable, flexible system for fast synthesis of nitrates and nitrites. Can meet on-site crop demand in requisite amount as and when required. It avoids safety hazards and costs related to requirement of continuous energy sources, pressurized environment for synthesis, regulated storage, refrigeration need, transport of raw materials and distribution of fertilizer. So all these are avoided, and that reduces the cost component drastically. Now finally I will come to one application, real application case. This is a maize. It has been grown using the plasma fertilizer, and this is called control, where we have only given water at regular interval, but we have not given any fertilizer. And you see that in the fruiting stage we are seeing that the very visible, the cones are grown over here, and in the control where we have applied regular watering but no plasma fertilizer, you see that no such corn is grown over here. This is exactly visible and directly captured using the camera. So this speaks about the effectiveness of the fertilizer that is produced using your thermal plasma. So this is one where various plants are grown, flowering plants using this plasma, and you can see that extra large flowers, vigorous branching, then growing in multiplates, then the size double the typical size that has been shown here, then extra large leaves, you can see the leaves. So it has effects, but different plants have different intake of this nitrate fertilizer, so and different times they need to apply. So for every plant the application interval, dose will be different. So all these things need to be studied well before you decide to apply that for a particular crops. So the doses need to be defined, the application route. Sometimes you get a better effect when you spray over the leaves rather than giving at the roots. So whether it is suitable to give it spray over the leaves, or we should apply it through the roots. So all these need to be studied in this area, and they are being done at present. So I have shown you only some of the interesting applications of thermal plasma and cold plasma in various areas, and you now probably understand what immense effect the plasma can impart to our society. So I hope that you have enjoyed the course, and whatever you have learned from this course will be very useful for your future venture, and you will be confident to apply the plasma technologies in the various areas where you want to expand. Thank you very much for attending this course. So this is the end of the course, and I wish you all the success for your future ventures. Thank you very much.